screen. Let us start today's lecture by going through certain older topics or by recapitulating some of the older topics itself. What we have here is, first of all, we have a Cartesian coordinate axis x, y, z. And there we have PQ is a line with direction cosine nx1, nx1, ny1, and z1. And PR, P and R be another line with direction cosines nx2, ny2, and z2. Now, so this is the PQ, this is PR. It has a direction cosine nx1, nx2, nx3, nx1 along x-axis and y1 along y-axis and nz1 along z-axis itself. And PR is another line, another straight line, which has direction cosine is equal to nx2, ny2, and z2. Now, theta is the angle between the two line segments before the deformation itself. Say after the deformation, the line segments became P dash, Q dash, and P dash, R dash like this. And theta, interpolated angle theta is changed to theta dash. We can determine theta dash from the results of analytical geometry. Cos theta dash nx1 dash nx2 dash plus ny dash ny1 dash ny2 dash plus nz1 dash plus nz2 dash means the cosine of theta, the individual angle between this is individual multiplication of the cosine vectors of individual line elements in terms of x-axis, in terms of y-axis, and in terms of z-axis itself. Now, the values of nx1, nx1 dash, ny1 dash, and nz dash, all these values, all these direction cosines values are given by our earlier direction cosines of other equation already derived, where nx dash is equal to 1 by pq, 1 by 1 plus pq multiplied by 1 plus dy dux by dx into nx plus dy dx into dy and into ny dux by dz into nz. And similar is the case with ny dash and nz dash. So the equations for our cases will be nx1 dash, nx2 dash, and ny1 dash, nx2 dash, and nz1, nz2. We have to convert this equation and we can make the addition like this. Thus, what we will have 1 plus EPQ plus 1 plus EPR, because it is the elongation of the line PQ, this is the elongation of the line PR, and multiplied by these other factors given in the equations itself. So 1 plus 2 EX, NX1, NX2, etc. Now, in particular, here you see the lines are given in original direction NX1, NX2, NY1, NY2, etc., but not with the dash itself. So this equation divided makes all these NX1 dash in terms of NX1, NX2, etc. This is very clear. Here's example. I need not explain it again. Now what happens if the two lines PQ and PR are right angles to each other before strain? Then what happens? Then after the strain, what will happen? All the lines containing NX1, NX2 multiplied by 1 here, NY1, NY2 multiplied by 1 here, and NZ1, NZ2 multiplied by 1 here. These three components, if we add it together, will become equal to 0. Because we know cos 90 from this equation, if I know that cos 90 is equal to 0 itself. If this theta is somewhere becomes equal to 0 due to some position of nx1 and nx2, so this multiplication from analytical geometry will be equal to 0 itself. So that for three terms are removed and the remaining terms remains like this. This is the equation for theta dash. Now, what happens? What happens here? Here nx2 now cos theta 1. Now cos theta minus 90 degree represent the change in the initial right angle. It is denoted by alpha itself. So first of all, it was in right angle. PQ and PR in right angle. Now after deformation, the right angle is changed. That becomes 90 degree minus theta, which is the change in new position of the initial right angle. And if you denote it by alpha, then what happens? Theta dash will be equal to okay, just 1 second. The theta dash will be equal to 90 degree minus theta dash, not theta, represent the length in the initial right angle, and this will becomes 90 minus alpha itself. It is not x but alpha. It is not clearly open out. Stop share. Now, now what happens? This cos theta dash will cos 90 degree minus alpha is equal to sin alpha, or all of this equal to alpha itself. So sin alpha is extremely small. So therefore, the earlier equation gives us the shear strain alpha between PQ and PR, and if we replace the direction of PQ and PR by x dash, at P by x dash and y dash axis, then x gamma y dash P cos theta dash will be equal to P cos theta dash. Expression given in the earlier this equation like this. Now let us use this notation in our present problem itself. The principal axis of strain remains orthogonal after the strain itself. Means the principal axis of strain remains 90 degree and after the strain itself, means due to the so the principal axis of strain remains orthogonal after the strain itself. Means what do we mean by that? The principal axis, all the strain acting over the principal axis itself, all three mutually perpendicular principal axis, they have the in between angle is always 90 degree, and we will prove that after the strain, after the deformation of this particular element due to the application of some external force, this 90 degree angle remains same before and after this deformation event itself. Now, if PQ is one of the principal extension of strain axis, PQ we know we have defined as a displacement vector, and his nx in his direction cosines are also defined here. But now if we think, if it is one of the principal extensions or principal expansion or compression or strains axis, means with direction cosine x1 x1 etc., then the equation nexx minus e1 into nx eyy minus e1 n2 is n2 etc., means the extension along x-axis, extension along xy axis, extension along xz axis. Actually, these are the shear stress itself, but we are replacing it in tensile stress form. Same is in xy and what, and eyy nz, etc., eyz nz1 etc. It ex2 into nx1, ex2 n1, and ezx minus epsilon into nz1. Here Ex is strain along x-axis, strain along y-axis, and this is strain along z-axis. Uh, this should be ZZ, not x itself. Each ZZ axis is minus epsilon is equal to 0, where epsilon is the total strain happens in along the PQ axis, PQ line itself, and these are their components itself. These are all their components. Now, if nx1, n nxz, nyz, nzz, etc. are the direction cosine of PR, uh, direction cosine of PR. Hence, we got another line which is intersecting the PQ line at P, and it has direction cosines nx2, nx1, nx2, nx, ny2, nz2. Now we know that nx1 into nx2 plus ny1 into ny2 and hz1 into nz2 is supposed to be equal to cos theta, and if it is 90 degree, it will be equal to 0 itself. Now multiply equation 4b, 40b given above by nz1, nx1, x2, etc., and then the equation will be take this particular form exy, ny, etc., and eyz, ezz, nx1, ny2, etc., ny2. This particular form will be achieved here, while we are multiplying this one with nx2, this one with ny2, while this one with nz2, and add them together. This equation will become like this, and if we use this multiplication of this formula nx1 nx2 plus this thing equal to 0, then this equation after addition will take this particular form itself. Then multiplying by 2 and putting 2xy here, there 2xxx yy zz, but there is xy 2exy is gamma xy, 2eyz is gamma yz, and 2eyz hzx is equal to gamma 2z, because we know along the principal axis, or the maximum value of shear stress is exactly half of the corresponding tensile stress itself in any plane or in any angular axis itself. Now if we put them together, put them in respective places, say here, like this, and we'll get the nx one like this, exx nz is 2 eyy ny1 ny1, this is like this, gamma x1, this one, this multiplied by this and this. Now we know total portion of this is equal to 1 by, just I have told you earlier, cos theta 1, cos theta dash is equal to total value of this equation divided by 1 plus EPQ plus multiplied by 1 plus EPR. So if we multiply cos theta dash and multiplied by 1 plus EPQ, 1 plus EPR, this will become 0, because we have to know the angle in between will be equal to 90 degree, and it will be cosine will be equal to 0 itself, where theta dash is the new angle between PQ and PR, and after strain, since PQ, and to satisfy this equation, EPQ and EPQ, neither EPQ now EPR cannot be equal to 0 in order to make the equation to 0. So we have to make the equation only 0 only when cos theta dash is equal to 90 degree itself. The line segment remains perpendicular after, which means theta dash is also 90 degree. Initially theta was 90 degree. Thus we have got this equation. Now we are finding that theta dash is also 90 degree to satisfy this particular equation itself. So line segment remains perpendicular after the strain, and also since PQR PR is an arbitrary perpendicular line itself, the principal axis. So every line perpendicular to PQ before the strain remains perpendicular after the strain itself. In particular, PR can be second principal axis of stress. Thus, always here we see that the in between angle is 90 degree, then before strain, before the deformation it will be 90 degree, and after the deformation it will remain equal to 90 degree itself. Now, so we can say that as PQ is one of the principal stress, then PR is also another or second principal stress, principal axis of stress itself. If PS is the third principal axis of, if we repeat this above step again in terms of Z, and if PS is the third principal axis of strain as compared to PR and PQ, it remains also perpendicular after the strain, after the strain itself. So therefore at P, we identify a rectangular element with faces normal to the principal axis of stress that will remain rectangular after the strain itself. This is because, say, we have a three axes PS, PQ and PR mutually perpendicular to each other, because we have proved that it will be like this. And if we make a cube or rectangular element, or a rectangular element with face as per PQ, PR and PQ, PR and RS, then that will remain rectangle after the strain also. When rectangle remains, it was in the form of rectangle, and the in-between angle is not changing. That rectangle remains exactly the rectangle itself. It is not become a rhombus itself. Now let us go for strain rosette. What is this? I have discussed this earlier. Like stresses, strain has to be shown graphically itself. How we have represented the stresses graphically? Just remember that it was we took the help of mode circle itself. So we have considered a prismatic block, and it contains an intersecting plane which intersects the prismatic block by an angle theta, and it has it is multiplied, say, two mutually perpendicular axes. It has normal stress and shear stress in between the two mutual axes, and we have to calculate what is the normal stress and shear stress in the plane which is at an angle, say theta, with the longitudinal x-axis itself. And this can be derived analytically, and this can be derived by means of a graphical also. How will it derive? It will derive by use of mode circle itself. But here, all these forces, or all these rectangular elements, all these prismatic bars are in two dimensions itself, because we always think that the prismatic block has a unique thickness. It actually is like a piece of paper, not like a cube. But now but this procedure, as it can use in two-dimensional stress to calculate the two-dimensional stress, and if possible, it is also possible to calculate the corresponding strain. This wearable procedure may be used while employing electrical resistance strain gauge, and instead of drawing the direct and shear stress on any new two partial places, we can obtain three and more direct stresses. We can calculate, we can measure on any three or more known direction itself on an exposed surface. Say surface a block is given, we have set three or more direct strain, and by employing three or more strain gauges in different electrical strain gauge, resistance strain gauges, and get the value of strain within few microns. when this particular body is under certain value of the force itself. A group of these gauges is at a point in specified direction itself. This group of gauges is defined as strain rosette. Actually, what they are doing, this is nothing but a measuring device which measures electrical strain, means movement or deformation of the body in a particular direction per unit length of the body itself in terms of resistive resistance. And a group, not a single one, but a group of these stresses are fixed in the specific different specified direction, and we can take the strain to know that to have the strain condition along the direction itself. Before going to the details, let us discuss what is the type of strain, what are the defined type of strain sources. Theoretically, the angle because the strain sources in a strain gauges in a strain rosette could be anything less than 360 degree and more than 0, which means if we want to set the strain gauge, the angle between them must be more than 0. It cannot be equal to 0. They cannot be set in the same straight line. It is of no use. And maximum we can set them to another 360 degree total clockwise rotated way. Anywhere you can place these strain gauges except the initial position when it is 0. You can place there. You cannot place it on 36 degree, 360 degree also, but any other angle in between 0 to 360 degree. Now, for the ease of calculating a drawing, we have different customs for placing the strain gauges in different places. It is customary to use the common angles like 60 degree or 40 degree. Essentially, this avails all conditions of the equations as well. So we should keep the common angle between the strain gauge like 60 degree or like 45 degree. But still, there are different ways of placing the strain gauges. What is that? Three different rosettes, three element rosettes, means there is only three gauges. There is rectangular type, another is delta type, four element rosette. There are four types: rectangular type again, and delta. Take delta rosette itself. Just 1 second. Hmm. A three element rosettes, the rectangular type. Okay. Now what is this? Three element rectangular rosette itself. What we are doing here, x, that is, this is O, you can say O, this is OA, OB, OC, and this is the x-axis and this is the y-axis. So OA is along x-axis and OC is along y-axis itself, and theta c, the in-between angle between OY and OX is equal to 90 degree, and theta b, the in-between angle between B and A is 45 degree. This is the three element rectangular rosette itself. If there is four element rectangular rosette, this is the rectangular rosette itself. So you have to pick like here, and like here. This is 45 degree, this is 45 degree, and in between that is 90 degree itself. If there is four element rectangular rosette, what we'll do? We one here, 0 to O to A, O to B, O to C, and O to D. What is the in-between angle? Here, theta B is equal to 45 degree itself. And angle from here to here, this is from here to here, this is equal to 90 degree itself. And angle from OA to OD, this becomes 90 degree plus 45 degree equal to 135 degree. Means this is also 45 degree from here, but from here it is 135 degree. This is OC, is 90 degree from OA, OB 45 degree from OA, and OA remains along the x-axis. So two rosettes are fixed along x and along y-axis. Next comes the delta rosettes. This is the process of physically placing the rosette itself. One is like this, another is like this, and A is like horizontal, B is at an angle. Let us see what is that, and C is at an angle itself. So what we are doing, we are having three rosets, not four. So one rosette is showing along x-axis, that is OA. Another is showing along OB, which is along, this is the rosette itself, and another is showing along OC. So what is OB? What is theta B? This is equal to 120 degree. Means this is 90 degree itself between the x and y axis plus 30 degree itself. So OB is inclined by an angle 30 degree with OY, and OC is equal to 240 degree. Means another 120 degree itself from theta B itself. So from here it is 240, 90, 180, 180 minus 240 minus 180 means is equal to 60. So this is 60. From here, this angle is equal to 30 degree, and here from this angle from the horizontal is equal to 60 degrees itself. So one is set along x-axis, which is along 0-axis you can say. Another is set placed along 120 degree from OX. Another is placed 240 degree from OX, or and second is placed 30 degree from OY, and third is placed 60 degree from the negative direction of OX itself. This is defined as delta rosette. Fourth, and last but not the least, this is T delta rosette. How it is work like? Looks like a T in certain cases, like this, and this. O is horizontal, B is like a certain angle, C is an angle from it, and D is the vertical itself. So what we are doing, we are putting one strain gauge along OA, that is become 0 degree. Next strain gauge D, it is the fourth strain gauge. It is put it vertically from A, that is OD, that is equal to 90 degree, and OC is equal to 240 degree itself, and it's from here OC comes here, and OD, OB. OB is not given. Let me see. Just 1 second. OB is supposed to be just 1 second. So OB is not given even here. So we can say it is around. So it is not, there is no fixed cut angle between them. So one is has fixed position, that is along X. Another is along D, that is the second fourth. Another is making 240 degree from A, and possibly 240 degree from here to 180 degree means 60 degrees away from 60 degree, and this is possibly the 45 degree away from this negative X or positive Y itself. Now straight process can be analyzed in the figure in the next page. In the next figure, what we have from our strength of material practice, the principal strains along 1 and 2 is along place 1, that is maximum strain, and 2, that is minimum strain. Ex plus Ey divided by 2 plus minus half into square root of Ex minus Ey whole square plus gamma xy, where Ex the strain along x-axis, dy strain along y-axis, and Ez and gamma xy is the shear stress among on acting on both x and y axis itself. And tan theta, the angle, theta is the angle which can be is given, which is the maximum value of the oblique plane, where which the strain is maximum, except for which this principal stress occurs, or so for which the strain is maximum or minimum itself. Now, therefore, now these two equations can be used to find the magnitude and direction of principal strain. So if we know Dx, Ey and gamma xy, you can safely calculate theta as well as epsilon 1, 2. But for example, if we have a three-elemental rectangular reset, then the equation three-element rectangular reset, then the equation ER is equal to cos ES cos square del u by dy cos theta sin theta ui sin square theta but du gamma by dz cos theta sin theta. Then epsilon A is equal to epsilon xx, epsilon B is equal to half epsilon A, epsilon xx, epsilon B, half epsilon xx, epsilon y, epsilon gamma x, and epsilon C, gamma y, gamma double y, and gamma xy, 2 epsilon B minus zeta. This, by using this equation, let how this equation happened. We got the three-elemental matrix here. Now you see the oh here. Now if we consider three-element rectangular rosette in like here afterwards, it will be shown in next pages itself. Now what happens where now the magnitude and direction of principal strain. For example, if we consider the three-element rectangular rosettes, then the equation itself the equation here epsilon r is equal to epsilon x cos square theta dy dx dux by dy cos theta cos theta ui sin square theta and d gamma by dx cos theta sin theta, where a xxy eb half ex ey plus dz and ec e gamma by y and gamma is eb ea and ec. Then by using the above equation, the principal strains are converted into this position itself. Similarly, other cases can be treated itself. Now, well, in the case of 5-element rosette, we have one extra strain gauge itself, which is strictly not necessary but used for checking purposes. This one of the strain gauges is defective. If then in a 3-element gauge, there is no way to check the reading and get the correct result. In a 4-element system, verification is always possible. For example, in a rectangular rosette, the angles are say 0, 45 degree, 90 degree. The gauges A, B, C, D. This configuration gives a quick check. And from the expression of the lateral fast variant, we have J1, EXX1, EXY, EXS1 and UXY, and is equal to EA plus EC into F sub B plus F sub D itself. This gives an independent check on the accuracy of all the strain check itself. Now the mass fit construction. What is have here? The construction is known as Murphy's construction. Here we construct a mode cycle for strain with the help of three direct strain and as above, and suppose the strain gauges A, B, C are oriented as shown in the mutual angle ABC. Here 1, 2, 3, 4. There are four angles. We can set four strain gauges here. If alpha and beta, between the alpha and beta, this angle and this angle is equal to phi with the unknown angle of the gauge A. Then with the principal strain, along with the principal strain direction. Now to construct a circle of strain, first draw a vertical line representing the y-axis itself like this, OY and OX. Then measure EPSA A, EPSA B, EPSA C. Eccentric strain gauges are in x-axis, y-axis. In all the measurements should be in y-axis first, and directly parallel, draw parallel vertical lines for each of them as shown is here. So here x1, x2, x3, this is here we have draw a particle EC. This is equal to EA. This is AB is equal to EA itself. So this point we have measured. We put the reading. This point we got by putting the reading in the strain gauge. This point we got putting the reading in strain gauge C. So we got the verticals here. First, take any point P1 on the AB line itself. Means this line is the AB line. We take a point P1 here. Sorry. And draw P1, P2 and P1, P3 at angle alpha and beta. Then what is P1, P2 and what is P1, P3? Let us see P1, P3 and P1, P2 by an angle with an angle alpha here, with an angle phi, with an angle beta here, because here OA, that is EB, this is the strain gauge at EB. We have plotted the value of the strain gauge here, and this angle is separated by an angle alpha. So we separated an angle here and drop a straight line here, and we separated another angle equal to phi, which is alpha A is drawing with alpha is drawing with x-axis. This phi we have projected here. This is beta, not phi. So from BC, we have put this in between angle beta, and we plot the beta here. That's what we got plot. So what you have got, any point on P and P, and drop P1, P3 at right angles to right angles alpha to alpha and beta. So we have got P1 and P2, P1, P2 and P1, P3. P1, P2, P3 at angles alpha and beta to cut EPSA A and EPSA C lines at P1, P2 and P3. This line, if we drop with this angle, if you drop this line will come and intersect this EPSA A line at P2. This line will come and intersect this EPSA C line at P3 itself. So P1, P2, P3 line is transformed. And this gives us 3 points P1, P2, P3, and circle drawn through them will be required the mode circle itself. OX1 and OX2 will be the principal strain. OX1 is OX1 is the principal stress, the minimum. OX2 is the principal stress, that is the maximum. And with the principal strain and phi, the relocation of EPSA and EPSA1 and EPSA A, this is a good construction, but particular cases of strain losses is very important itself. So quickly recapture this thing again. What we are doing, we are having the strain gauges placed like this: one strain gauge at A, at B, at C. A is making an angle 5 is the EPSA axis, and EPSA B making angle beta with the A, and EPSA C OC making angle beta alpha with OB is making angle alpha with A, and OC is making angle beta with A. So what we drop, we got a point P1 here as per any direction itself. There you go. We got the point P1, dropped the N. Then what we have grouped, we plot this axis OX and plot this axis OY itself. From OA O dropped, find out the point OX means the value of the strain gauge along X1 itself, along the C gauge